Welcome to Circuit Secrets. In this video, I'm going to take you line by line through the source code for a CNC motor controller that will allow you to use DC motors with a CNC machine. The source code for the controller in this video can be found at www.circuitsecrets.com. If you have not seen it, there's another video on my channel giving a basic explanation and demonstration of how this style of controller can be used to control a DC motor with GRBL. This controller design works with a GRBL control board. It is designed to run on an Arduino Nano with an H-bridge, DC motor, and a home-built infrared encoder. A 3-axis CNC machine would require each axis to have a separate Nano-based controller and associated hardware. If you enjoy this content, please don't forget to like and subscribe. Now, into the source code. In the first line, we include the AVR interrupt header file. This is a pre-compiler command to include the library that contains the code for dealing with interrupts in the AVR series of microcontrollers. The AVR series is the 8-bit microcontroller family that is commonly found on Arduino boards. An interrupt is a way for a program to perform a task only when a specific event occurs, such as a change in voltage on a pin of a microcontroller. The .h indicates we are including a header file. A header file contains links to the library and information such as function declarations relevant to the library. Next, we come to some static definitions indicated by the define statement at the beginning of each line. Definitions are substituted by the preprocessor before the source code is compiled. Definitions are handy as they allow easy-to-understand words to be replaced by numeric values during compilation. This makes code easier to read, like named variables, but results in a smaller memory footprint once compiled. Many of these definitions can and should be changed based on your hardware configuration. The first definition is overrun limit. This value determines how far the actual track position read by the encoder can be from the target position, calculated by reading the step and direction signals from the GRBL board. When this value is exceeded, the motor controller will stop the motor by putting the H-bridge into its stop state, and the built-in LED on the Nano will flash to alert the user of a tracking error. This is to prevent a runaway condition on an axis. For my hardware, I set the overrun limit to 160. 160 steps is 1/2 of a rotation on my encoder, or a movement of 25 thousandths of an inch. The next definition is motor maximum speed. This definition can be used to limit the maximum speed of the motor. The max value is 255 and coincides with the limits of the variables used for PWM, pulse width modulation, on the Arduino Nano. This value can be used to slow the motor down to correct encoder problems such as skipping steps. The next value is the motor minimum speed value. This definition sets the lower limit of H-bridge output to the motor. Every DC motor is a little different, and each drive system will have a slightly different amount of mechanical resistance that needs to be overcome to move. For my windshield wiper motors, a setting of 70 seems about right. Different setups may require different values. The next definition is the oscillation dead zone value. This is a limit of resting precision used to prevent drive oscillation. Drive oscillation in this context is when the drive tries to come to a stop, overshoots the stop point, overcorrects and overshoots in the other direction, and bounces back and forth. With my hardware, I used a limit of 2, which means the drive will come to rest within 2 steps either way of the target point. This gives me a precision of plus or minus 0.3 thousandths of an inch when the drive stops. This precision is far better than the accuracy of my machine. The next set of defines uses predefined Arduino pin names and substitutes them in turn to allow easy-to-read naming for the pins. GRBL direction is connected to the axis direction control pin in from the Arduino running GRBL. GRBL step is connected to the axis step pin from the Arduino running GRBL. GRBL pause pin is connected to the reset abort pin on the Arduino running GRBL. The 2 detector pins are connected to the IR detector diodes for the encoder. The emitter pin is connected to the IR LED used by the encoder. The 2 H-bridge PWM pins are used to control the H-bridge. Next, we come to the function declarations. Function declarations tell the compiler what functions are defined later and the type of data the functions will take as arguments and return data types. Function declarations are a handy roadmap that can be used to see how a program is broken down into its building blocks. These declarations specify the functions forward, backward, stop motor, encoder logic, alarm control, and alarm 1. The function forward contains the code to cause the motor to turn in direction 1 or forward. The function reverse contains the code to cause the motor to turn in direction 2 or backward. The function stop motor contains the code to cause the motor to stop turning. The function encoder logic contains the code to deal with changes in the encoder state and tracks the changes. The function direction logic contains the code used to set the motor direction based on the current position and the target position. The function alarm control contains the code to call an alarm. It was designed to allow multiple alarms or error codes, but as of right now there is only one out-of-bounds alarm. The function alarm 1 contains the code used by the out-of-bounds alarm. Next, we come to the global variables. A variable is a piece of data that contains a value that can be both read and wrote. A value that can change as needed and can be accessed by other code. Global variables can be accessed by any function and they persist through function calls. A global variable differs from a local variable in that a local variable inside of a function is reinitialized every time the containing function is called. The first global variable is alarm trigger. This variable is of the type Boolean, meaning that it can only be true or false, 1 or 0. A Boolean is the smallest variable possible as it only takes 1 bit. The equals sign is used to assign a value to the variable. In this case, that value is false. False is a keyword that substitutes to 0. The next global variable is the integer difference. An integer is a variable that holds a number. With Arduino Nano, that number is a 2-byte 16-bit number with a value between negative 32,768 and 32,767. This variable is used to track the difference between the target point and the actual point. It is used for motor direction logic, motor speed regulation, and as a test for the out-of-bounds alarm. The next variable is encoder data previous read. It is used to store the last read of the encoder for comparison to the current encoder state. This allows a determination if the drive has moved forward or backward. Next is the encoder data variable. This variable holds the current state of the encoder. Next is the GRBL step data variable. This variable holds the step value data read from the step and direction pins connected to the GRBL board. Next is the actual point variable. This variable is changed based on encoder input to keep track of the physical position of the axis. The next variable is the target point integer. This variable keeps track of steps sent by GRBL to establish an axis position target or where the actual position of the axis drive should be. The actual point and target point are compared and used together to make decisions about motor movement and speed. The next variable is the motor direction integer. This variable holds the desired state of the motor and is used by logic to control the H-bridge accordingly. The last global variable is the speed limit variable. This variable holds the motor speed limit, which is based on predefined constants. With this variable positioned in the global variable area, it is not only available to all functions, but the calculation is only performed once when the program begins. Next, we come to the setup function. This function is run once when the board first starts and is usually used for configurations such as timers, interrupts, and pin modes. The first section of the setup function I use to set pins to input or output. The first 2 pins are used to control the H-bridge, which controls the motor. An H-bridge has 2 control pins that are used to control the direction and through PWM, pulse width modulation, the speed of a motor. Setting these 2 pins as output allows us to send a PWM or ground state to the H-bridge. An H-bridge also has an enable pin that can be used by a microcontroller to enable or disable the H-bridge. I hardwired the enable pins on my H-bridges to keep the program as simple as possible. Next, the pin for the built-in LED is set as output. The LED is used to indicate the encoder state and indicate tracking problems. Next is the set of pins used by the encoder. The emitter pin is used for the infrared LED and is set to output. The two detector pins are set as input and are used to read the infrared detector diodes used by the encoder. The next group of pins are used for communication with the GRBL board. GRBL direction and step are used to read the step data coming from the GRBL board. One pin reads the direction and the other the step pulses. The GRBL pause pin is used for sending a reset command or low state to the GRBL board if an error in tracking occurs. For now, we set the pin as input, and when an alarm is triggered, the pin is set as output and pulled low. Next, we call the digital write function. This function, when used on a pin set to output, sets the state of the pin. When used on a pin configured as input, it can activate the built-in pull-up resistor. A pull-up resistor is used to pull the logic level of the pin high so the external circuit can cleanly pull it low. This is the standard practice with most digital circuits, as pulling low is less susceptible to noise than an external circuit pulling a pin high when tripped. We set the pull-up resistors on all three GRBL pins. Then we set the pull-up resistors on the infrared detector diodes for the encoder. Next, we turn on the infrared LED for the encoder by setting the pin state high. Now we set the H-bridge pins low to ground both sides of the H-bridge control. In this state, the H-bridge is passing ground to both terminals of the motor, which acts as dynamic braking if the motor is turning. Instead of the charge generated by the motor being recycled as is common with regenerative braking, it is simply dumped to ground in a short circuit fashion. With larger than needed H-bridges, this is fairly effective, but could result in damage if the H-bridge is running at its absolute limits. I use 43 amp H-bridges with motors that barely draw 3 amps at 12 volts. I have run my test machine for 24 hours straight and the H-bridges don't even get warm. Now we get into the interrupts portion of the program. First, I clear all interrupts with the CLI function to ensure the interrupts are all cleanly set. Now I call PCICR, the pin change interrupt control register. I set bits 1 and 2 to 1 with a bitwise OR assignment. Bit 0 is port B, bit 1 is port C, and bit 2 is port D. So this enables pin change interrupts on port C and port D. Next, we set the PCMSK1 value with a bitwise OR command. PCMSK is pin change mask, and PCMSK1 indicates it is the mask for port C. PCMSK0 is port B, and PCMSK2 is port D. Setting the mask tells the interrupt system what pins on the given port to respond to. This is important to set if you're not using the entire port and are leaving pins disconnected, as their logic level can change and needlessly trigger the interrupt handler. We set pins 0 and 1 of port C to trigger the interrupt handler. Port C pin 0 is analog 1, and port C pin 1 is analog 2. These are the pins connected to the GRBL board, so step pulses or direction changes will trigger the interrupt handler. Next, we set the PCMSK2 or pin change mask 2 port D masking to enable interrupts on port D pins 2 and 3. Port D pins 2 and 3 are digital pins 2 and 3. These are used to read the encoder. In the next line, we call SEI to set the interrupts active. SEI is the partner function to CLI, which turns off the interrupts. The last line of the setup function we use to grab the current state of the encoder, so we will have valid data to compare when the encoder's interrupt is triggered. We use the port read capability of the Atmel processor because it is faster than 2 separate digital reads to collect the information. To do a port read on port D, we use PIND. This stands for port input D. The ampersand symbol means it is a bitwise AND read. This means that any bits of the port we set as 0 in the call will return 0 no matter what that pin's value is, and only the 2 pins we set as 1 will return 1s, and only if the state of that pin is 1. This can be thought of as masking some pins off, so we simply ignore the pins that our mask says are 0 or ignored. To further complicate matters and make this interesting, we are not reading pins 0 and 1, but pins 2 and 3. This is a binary read, so pins 2 and 3 will return 0, 4, 8, or 12, depending on the state of each pin. We could use bitwise shifts to convert the output to 0, 1, 2, and 3, but that would complicate things further. The value is stored in the variable encoder data previous read. The setup function ends. Next, we come to the functions which contain most of the logic for the program. The first function we come to is the forward function. This function handles forward movement of the motor. This function takes no arguments and returns no values. This is indicated by the void keyword. First, we have a conditional if statement. An if statement is a conditional statement that controls the execution of a block of code. This if statement tests to see if the motor direction variable is set to 1. The motor direction variable indicates to the program the current state of the motor. A value of 1 indicates the motor is turning forward. When the motor is turning forward, the pin to the second PWM pin on the H-bridge needs to be set low. This if statement checks the motor direction. If it is not set to 1, the code runs, sets the motor direction variable to 1, indicating forward, and sets PWM pin 2 low. Next, we come to an if statement that acts as a motor speed limiter. We compare difference with the speed limit, and if the difference is larger than the speed limit, we then temporarily reduce the value of difference. We limit this because the maximum value the microcontroller can send to PWM is 255. We also use the limit if the encoder cannot keep up with the motor. The speed limit variable is set at the top of the code. Next, we use analog write to set the PWM pin 1 output. We use the difference variable added to the motor minimum speed variable to set the speed of the motor. The motor minimum speed variable is the lowest value that will allow the motor to turn. This is the end of the forward function. Next, we come to the backward function. This function controls the reverse motion of the motor. This function is structured exactly the same as the forward function. The notable differences are the change to the motor direction variable and the reversal of the H-bridge PWM pins. For reverse motion, the value of the motor direction variable is -1. H-bridge PWM pin 1 is set to low, and PWM pin 2 is given a PWM signal to set the speed. The next function is the stop motor function. This function sets both H-bridge PWM pins low and sets the motor direction variable to 0. Now you can see the motor direction variables equal 1 for forward, 0 for stop, and -1 for reverse. The next function is encoder logic. This function, like the others before, takes no arguments and returns no value. This function deals with encoder logic and tracking the actual position of the drive. In this function, the first thing we do is call a port read for the encoder. We use the same masking as we did in the setup to load data into the previous encoder state variable. We store this data in the encoder data variable. Now we come to the actual logic used for tracking encoder movement. I showed you the encoder has 4 possible states during the explanation of the encoder in the setup function. To recap, the possible states of the encoder are 0, 4, 8, and 12. We need logic to handle changes from each state to any other state. We use the encoder data previous read as the reference for the last position of the encoder, and the encoder data variable to store the current state. We read fresh data into the encoder data variable at the beginning of this function, and we will use that data for logic to determine if the encoder is reading forward or backward movement. We start with encoder state 0. If this is the case, the first set of logic runs. The first if statement inside the encoder state 0 if statement tests if the previous read is 4. A read of 4 when reading only bits 2 and 3 looks like 0, 1, and the current reading of 0 looks like 0, 0. This logic runs when the encoder goes from 0, 1 to 0, 0, meaning the IR detector on the left was exposed to the IR emitter and the detector on the right was blocked, but the encoder wheel moved to expose both detectors. If the encoder wheel had moved the other direction, the encoder would have gone from 0, 1 to 1, 1, meaning both detectors are blocked by the encoder wheel. We decide one direction is positive movement while the other direction is negative. This is arbitrary, and if it is backwards, simply reversing the H-bridge or motor wiring will correct it. Once the correct polarity is found for interaction between the motor and encoder, the GRBL parameters can be changed to invert the system if it is running backwards. To find the correct polarity of the motor in relation to the encoder, the shaft is turned slightly by hand. The motor should fight to correct the position and return the encoder to the previous state. If a manual movement of the drive and encoder wheel results in the motor picking up speed and running in the direction the encoder was turned until it trips an out-of-bounds error, stops and flashes, you know the motor or H-bridge is wired backwards. When the step of the encoder is detected, the value stored in the actual point variable is changed to reflect the movement. If the encoder changes by one step, the actual point variable is incremented or decremented by 1. If the encoder changes by 2, more logic is needed to determine the direction of movement. A step of 2 indicates the encoder is spinning too fast for the changes to be read accurately. If this state occurs, we check the current direction of the motor and increment or decrement by 2. After the change is made to the actual point variable, the value stored in encoder data is copied to encoder data previous read. The rest of this function repeats the same process but uses the other possible encoder combinations. The next function is an interrupt service routine. This ISR responds when it is called by pin change interrupt 1. We learned in the setup function that interrupt 1 is port C. Port C is where we connected the input from the GRBL board. We use this function to track step commands. The first thing we do in this function is read port C into the GRBL step data variable. We use port in C the same way we use port in D for the encoder. Because we are using port C pins 0 and 1 to read input from the GRBL, the possible values are 0, 1, 2, and 3. Pin 0 we use as the step indicator, and pin 1 we use as the direction indicator. This means that pulses indicating forward range in value from 0 to 1, and values indicating reverse are 2 and 3. We only read half the steps as direction pulses. These are when the step pulse goes positive, so we only react to the values 1 and 3, 1 being a forward step and 3 being a reverse step. We increment or decrement the target point variable based on this value. Next, we come to the ISR for interrupt 2, port D. Port D is the port the encoder is connected to. In this ISR, we simply call the encoder logic function, which we already covered. Next, we come to the direction logic function. This function makes decisions about motor direction based on the value of the variable's actual point, target point, and the definition for oscillation dead zone. It then sets the difference value used by the motor direction functions and calls the appropriate motor direction function. If the target point is greater than the actual point, then the motor has to turn in one direction to attempt to match the points. If the target point is less than the actual point, then the motor has to turn the other direction. If the difference between the target point and actual point is lower than the defined dead zone value, then the motor needs to stop. The next function is the alarm control. This function stops the motor, clears all interrupts, sets the GRBL pause pin to output, and sets it low to pause the machine. If difference is greater than or equal to the overrun limit, the alarm 1 function is called. This function can be expanded to include other alarms by testing other values with other if statements. The next function is alarm 1. This function simply blinks the built-in LED of the Nano to indicate the alarm state. Finally, we come to the loop function. This function is called repeatedly, automatically by the program. The first thing we do in this function is test to see if we have an overrun condition by comparing difference to overrun limit. If the difference is equal to or greater than the overrun limit, the alarm trigger is set true. If the alarm trigger is false, we call the direction logic function. Next, we check the state of the encoder and illuminate the built-in LED for half of the encoder states and turn it off for the other states to allow easy calibration of the encoder. An else block is matched to the alarm trigger false test. This allows alarm control to be called if the alarm trigger state is set as true. I hope you enjoyed and got something out of this video. The source code is available at www.circuitsecrets.com. Don't forget to like and subscribe.